So we are going to start talking about systems of linear equations. Systems of linear equations. And what that really means is instead of just looking at one linear equation, just one graph, one line, we're talking about multiple equations, multiple graphs, multiple lines. And you could look at as many as you wanted. We're just going to look at two for right now. Okay? So we're going to look at two linear equations. And we kind of think of them as like working together. And what that means what I mean by that is they're using the same variables. So now go ahead and draw 3 coordinate planes. 3 y-axis and 3 x-axes.
Are we ready? Are we doing that right here?
Nope, you're doing it on the back. On the back of that page.
Oh, okay.
So we've been looking at just one linear equation at a time. Like this one, or like this one. And now we're going to be looking at systems of equations. So that means that we look at both of them at the same time. Both of them at the same time. So we're looking at the way two lines interact with each other. How they work together. Can I scroll down? No? Not done yet? So I want you to think about, if we're looking at two different lines, how many different ways could they cross? 4? What ways? Show me. They can meet at 4 points? Yeah. So like you can use your arms as an example. You could either like stick your arms out straight, right? And they would never ever cross. These lines would never cross. Or I could cross them at one place, right? Or they could be the same exact line and they would cross in infinitely many places. But if I have 2 straight lines, can I like bend my arms so that they, I mean, I guess I can, but you can't, if you have 2 straight lines, they're never going to cross at more than one place unless they're the same line. So let's draw that out. So think about how many ways can two straight lines cross. So again, we can have two lines that never intersect. That never intersect. What do we call?
Straight lines. Can I just leave lines?
That's fine. So does anyone know what these are called? Lines that never ever intersect? Parallel, yeah. And we denote that by drawing two arrows. One there, two little triangles. These are, yeah, parallel lines. Parallel lines. And these never cross. Something to note about parallel lines, and we'll talk more about this on Monday, is the slopes of parallel lines are equal. The slopes will be equal. So we have our parallel lines, and then we have lines that cross just at one point. Let's draw that. We have 1 and 2. Lines cross, lines that cross at one point. Okay. And then one more is if we have two lines that are exactly the same. So a line, and then another line on top of it. Two lines. So these are the same line. Those are our three options of different types of systems of equations. Okay. So I want to go back up and look at those first three graphs that you drew. Can I scroll up? Okay. So when we have just a line, we've learned that every single point on that line is a solution to the equation. It's a solution to the equation. So let's pretend that this line is y equals, let's say, 2x plus 4, something like that. Every single point on this line is an ordered pair, right? It has an x coordinate and a y coordinate. And every single point on this line is going to be a solution to this equation. Every single point on this line is going to make this equation true. Same with this line. If we have, let's pretend this is y equals negative 2x plus 4, right? I know that this blue line had a positive slope because it's going up from left to right. This green one has a negative slope because it's going down. But again, every single point on this green line is an ordered pair, x, y. And every single point on this line can be plugged back into this equation and would make the equation true. Every single point on the line is a solution to the equation. Okay. So now when we have a system of equations, what do you think the solution to a system of equations would be? If the solution is every single point on the line, what would our solution be for this system of equations? Would it be every single point on the blue line and every single point on the green line? What do you think? Yes? You think so? No? You don't think so? So our solution to a system of equations is going to be this point where the lines intersect. The points where the lines intersect. This is the solution. Solution is the intersection. Solution is the intersection. So now going back down here, we know that the intersection, the place where the lines cross, is the solution. How many solutions do you think parallel lines would have? If they never ever cross, how many solutions do parallel lines have? 0. Yeah, there's no solution. And then what about lines that cross at one point? How many solutions does that system have? Just one. Just one unique solution. And then what if they're the same line? How many solutions would we have? How many points are there? How many points are on a line? More than 2.
Wait, they don't know. That's what I said. They don't know. Isn't a line infinite?
Yeah. So if they're the same line, then we have infinitely many solutions. Infinitely many solutions. Okay. All right, so I want you to hold on to those note pages, to that note page, and we're going to come back to it again on Monday. If you don't have a safe place to put it, you can turn it in and I'll give it back to you on Monday. Right, and then we're going to flip over to the tree growth page. Tree growth. Right, and so what we're looking at here is this gal named Polly planted a magnolia tree and a pear tree on the same day. And we're going to model that real world situation, her like planting a tree. We're going to model that using system of equations, 2 different equations. One equation that shows the growth of the magnolia tree and one that shows the growth of the pear tree. Okay, and then we're going to compare them. So let's look at part A. I think I still need to open it. But I want you to look at part A. And you have a table there. The year is our x coordinates. The year is our x variable, our independent variable. And then the tree height is our y variable. That's our dependent variable. So you can go through and you can plot these points on your graph where the year is along the x-axis, the height is along the y-axis. Year is on the horizontal, height is on the vertical. So you should come up with 5 different points on the graph. Okay? And then once I get this open, we'll go over it together. So plot x and y. Year is x, tree height is y. So, one more time. Year is our x coordinate. Tree height is our y coordinate. X coordinate is independent variable. Remember, if we see time, if we see year, month, days, hours, seconds, if we see time, that is like 99.9% of the time going to be our independent variable. Time is always our independent variable because we can't control time. It just happens. And then y would be our dependent variable. Y is our vertical axis, x is our horizontal axis. So this first point here is at 0, 4. So 0 on the x-axis and then up to 4 on the y-axis. Then year is 1. When year is 1, tree height is 6. So that means my point is 1, 6. I go over 1, up to 6. Year 2, my tree is 8 feet. So my point is 2 and then up 8. At year 3, the tree is 10 feet. So I go over 3, up 10. And at 4 years, the tree is 12 feet. So I go over 4 and up 12. And then I can connect my points and draw my arrowheads. So I've just come up with one equation. Now let's look at our second equation. So this was our magnolia tree. Magnolia tree. Have you guys ever seen a magnolia tree? Do you know what it looks like? They're super pretty. I'll show you in a picture in a minute. Oh, come on. So now let's take a look at the pear tree. So the pear tree. This time they don't give us a table, they give us an equation. Let's think about this equation in slope-intercept form, where m, the coefficient of x, is my slope, and b is my y-intercept. So in this equation, what's my slope? What's my slope? 4. And what's my y-intercept? We don't really have a plus b here, do we? So if I what could be like an invisible number that I'm adding? Not 1, because if I add 1 to 2, what does it become? 3. 0, because if I add 0 to 1, what does it become? Just 1. So if I add 0 to 4x, what would it be? 4x. Yeah, so there's kind of like this invisible plus 0 there. So what's my y-intercept? 0, 0. That's my b. So that's my y-intercept. And then use your slope. Use your slope. My slope is 4. 4 is equal to 4 over 1, right? So my rise is 4. My run is 1. So from our y-intercept, we go rise 4, run 1. Rise 4, run 1. And be careful, look at the scale on the side. We don't just count up 4 lines. We just go up 4. Up to 4 and then over 1. Does that make sense? Okay. So draw your line. Draw your line. So we go up 4 over 1. Up 4 over 1. Up 4 over 1. Up 4 over 1. And we connect the points. Okay. Now part C, I'm going to have you do on your own for the next couple minutes. But I'll walk you through it. So we want to first look at the unit rates of the magnolia tree and the pear tree. So what that means is every year, how much does each tree grow? Every year, how much does each tree grow? And then decide which tree grows faster. And then, so that's part 1 of part C. And then I want you to copy your equations, draw your equations again on this same graph. So draw both your pear tree and your magnolia tree equations on this graph down at the bottom. And then circle the point where the graphs intersect. Circle the point where the graphs intersect. And tell me what you think that point represents.